Welcome. This is a gentle introduction to cross-compiling Restup program with the Rust toolchain manager Restup and the package manager Cargo. As a Rust programmer, we code and build an application in one host system, say Mac, and we need to offer it to distinct targets that include Mac, Windows, Linux, and even browser and mobile and embedded devices. This act of building an executable or binary in one host system in such a way it is executable in distinct targets is called as cross-compilation. We cross-compile a program for a couple of reasons. Many times the target machines are not powerful enough to perform the compilation activity that involves assembling the dependencies as specified in your source code configuration to create an executable. So we'll produce the executables from a powerful machine and will deliver the controlled copy to the individual machines. Many times you cannot afford to offer your source code. Another technical aspect is efficiency. This is a central theme for WebAssembly architecture, and we discuss that in the future sessions. The compiler creates a couple of common intermediate representations, IR, for the distinct class of targets during the process. Creating an executable from this intermediate representation to the target platform is very efficient rather than repeating the common activity on each cycle of compilation. So my preferred way of learning is doing rounds of experiments, creating as many errors as possible to obtain a better insight into the underlying mechanics. So what are the experiments I am planning to do? This is the plan for the experiments. So we are going to appreciate what really a cargo new does and what a cargo run and what a cargo build is really doing underneath and what a cargo build -hyphen release does. And then we are going to a release candidate will be available here, and which we are going to SCP into a Linux machine, and we are going to see what is going to happen when we are attempting to execute this executable. Then there is a concept called as a target triple that requires a small lecture, a boring lecture, and I promise you that it is not going to take more than 1 minute. And then we are going to make some modification to the tool chain by adding a triple target. We created a binary application, simple package. So if we put a LRA, this is the package created now, and I'm getting into this. So there is an src directory where our hello world program will be automatically placed, and the cargo.2yaml. Let us have a quick view into the cargo.2yaml. Nothing. It's a very simple cargo.2yaml, even without any dependencies or any other configuration except for the name. So there is not much we are going to do now in the cargo.2yaml. And if we examine what is there in the src, there is a main.rs. It has the famous println macro that tells you what is hello world. So we'll just make a change to this. Hello cargo and Restup, because those are the two friends we are going to master today. And let me start this, and back to the parent directory where the cargo.2yaml lives. So now cargo, I'll show you again. So these are the two directories, src and cargo.2yaml. Now we issue the command cargo run. So it's doing some building activity momentarily, and it is saying that it is finished, and then unoptimized plus debugging info, a target that has which is an unoptimized and debug info. Just observe this two outcome and running target debug simple. So it did a compiling, and the compiler compiled executable is an unoptimized one for the purpose of development or for the purpose of developer to do some debugging, and it also runs when you are giving the run. And so it respected, we made some changes to the default println, so hello cargo and Restup. That is a observation we are making from this experiment. And let us check what happens to the directory structure. Now you see that a new directory which is not available earlier is created, the name of target, and this is a target directory that houses the debug. Let's ignore momentarily the cache dir.tag and the .rustc underscore info.json, and let us get into this directory debug to see the members of this. Let me put it clear more frequently because the QuickTime video screen recorder is creating some, it won't give you much visibility. So ls-lra and cd debug. So this is what we are having here. So if you put here, so there is two more hidden directories, fingerprint and cargo.log. We will come to that later. Now this is a simple which is an executable. You see the X symbol here, so it is an executable, and the size is too big. It has been blown up with a lot of other information which we can strip on every later stage. Now we don't want to lose our focus here. So the idea is when you issue the statement cargo run, it does two things. It created this simple executable, an executable name itself is simple, and it runs this from this directory. So we can run directly this simple from here to say this. Okay, so this is what is the first experiment. So our first experiment is over. And what happens when let me remove this target cargo -v is forward boss, and when I issue the command just build instead of run, so you can see that it indirectly uses your Rust-C, and it passes all these parameters to the Rust-C, and it makes so that the cargo makes your life easy by doing all these things on behalf of you. And anything that we can observe from here that will be very useful for us. So just let us keep this here, and if we put this ls-lra, so now you are not seeing this hello Restup and the cargo because it is just a cargo if it be build. And let us get now the target directory is again created, which we have removed earlier, and if we get into this, and again we are having this debug. So earlier, and so there is no change between cargo run and the cargo -v build. Both of them are creating an unoptimized executable for the purpose of a developer. So that's it. So cargo run does an additional activity of creating this thing, and it is running this. So if you get into the debug again, so we are having the same simple, so we can execute from here. Okay, now we are done with these two experiments, cargo new, cargo run, cargo build, and let us now go to this cargo build -release. Let me remove this target directory again. This will be created every time we run automatically it will be created every time we run a build activity. So now I am going to provide a cargo build -release. Again, we'll put a -v here to understand. So now again it uses the Rust-C, there is only one way, and it has created something in the target release directory. So it is not putting that into the debug directory. And if you notice, this is a target release optimized. So it is not something that is for the dev. So it's more of like a production. It is, in fact, not more or less, it is a production. This is the way you create a production quality executable. So let us check that. Let's target release. So now again you are having a simple, and that is an executable, but again the size is too big that no one can accept that having (387 KB for a simple hello Restup and the cargo. So we can strip this later. So the process is called stripping the symbols and the constants and unused things that, though we are thinking that it is a release, production release, it still have certain symbols that we can strip off, and we will do that as the last leg of the experiment. So if we run this cargo build without any of this release, then you are having this def unoptimized plus playback info. So if we get into the target directory again, you will have both the debug, that is for the development purpose, and the release, that is for the production purpose. Okay, so this is also done. Now we are going to send this executable to a Linux machine. So let me go to the release again, and this is the simple that is available in my Mac system. So let me provision here, let me SSH into a Linux machine, which is a droplet. I got it from DigitalOcean. SSH So I have created a from Mac as a directory in the Linux box, and this is a Linux box, and this is our Darwin Mac box. Now I am going to SCP this simple to this Linux box, and I will attempt to run this simple from here. So ls nothing here. So let us get the PWD of this, which we can use it for our SCP simple, and root at rs.com. Okay. So now this is SCP into the Linux box. So now the simple is here, the Linux box. Let me execute this. Now you'll understand why a cross-compilation is required. Fine. So that is a conclusion. Now the idea is we have an executable that is created in a Mac environment, and that is not executable. You cannot execute this artifact in the Linux environment. That is a conclusion, right? Why? That requires a lecture. So the word executable is confusing to me. Let me use the word artifact for this, because executable is both an adjective and noun, I believe. How to make an executable in such a way it is executable in a foreign machine is called as a cross-compilation. So I will use this word artifact and executable interchangeably. So what is this target triple? So that is our next milestone. If you offer a gcc-dump machine, what it says is the architecture of this machine, which is an x86-64, Apple is the vendor and Darwin is the operating system, And if I go to the Linux box, if I execute this gcc -dump machine, it is telling you it is an x86-64. Red Hat is a vendor, the Linux is operating system. So x86-64, which is a 64-bit version of this x86 family of CPU. It should be either from the AMD or from an Intel. So it is a complex instruction set architecture, and probably may know about the other interesting architecture, which is powering your iPhone or Android device. That should be an ARM64, a cute instruction set architecture. It's a restricted instruction set architecture, and that kind of a style is preferred. You probably may know that it is for its low heat generation and minimal power consumption, and of course low cost. So for a person who is an admirer of an object-oriented approach, if it is, you can think of this x86-64, the instruction set architecture, as an abstract model. And the great companies like ARM is selling the license to Samsung and Apple to produce semiconductors, and let us just stop it here. We don't want to get into the licensing at this moment. So x86-64 is a family of instruction set architecture, which is an abstract model, and concrete implementation of this will be your CPU. And the second segment in the triple target, we call this as a triple target because it has three segments. The second segment is the Red Hat, and the third segment is operating system. So if you refer the Rust book platform support, they classify the targets into three tiers: a tier 1 architecture, and a tier 2 architecture, and of course they have a tier 3 architecture also beneath. And we will just focus our attention to this tier 1 architecture. So now our idea is, we are writing our application, building our code in this x86-64 Apple Darwin, and we want to port this to x86-64 unknown Linux GNOME. So the unknown here is an indication that it is not, the vendor is not important here. That is how we have to read it here. It doesn't mean that Red Hat is a very famous name, everyone knows it. So it doesn't mean that the vendor is unknown. It supports everyone or every target, and it is vendor independent. That is what the meaning is. And what to do now? So naturally we have to ask the Restup to add a new target for this. Otherwise it is not possible for us to release this. Let us see that in action now. Once I go to the plan. So now we done with this boring lecture. So we will try to release to this target using the cargo build -release -target to this target. Which target? This. So let me just copy it here. I go to the Apple machine. So you have this gcc dump machine is a command that if you know this already, otherwise just this is a way you can find what is a target system to which you have to dispatch or you are compiling for or releasing for. So now I give this cargo what is the thing -b, and then we are going to build -release, and okay, we have to do this from the place where we have the cargo.tm, otherwise it won't work. So let me remove this target again so that we can see this information unadulterated. Cargo -b build -release. Now we are passing the additional parameter target, and we'll pass this x86-64 unknown Linux GNU. So this is anticipated because I experienced this already. So when you are doing this, you will also experience this. experience an error and then you try to address this. This will give you a lot of insight when you experience a similar kind of a problem. This is a very famous thing, that is cannot find crate for STD. We will reproduce this later again in the Linux box. Many a time this cannot find crate for STD is because of an absence of a relevant target in the tool chain. So the suggestion by Cargo to the Restup is consider downloading the target with the Restup target add x86-64 unknown Linux GNU. Okay, so this process didn't exit successfully. Now wait for 10 seconds. Let me clear this and I'll show you what is this Restup Show. So when you execute a command Restup Show, it shows you that what are the installed tool chains here. So in the Linux box, if I execute this command Restup Show, it will tell you the active tool chains installed here. And there is a small issue in executing this Restup Show. It is not showing you this installed tool chains. In fact, it is having this tool chain that is installed, which is not displaying here. Let me try to show why it is not getting displayed here. Maybe a simple issue with the Restup. And let me focus back to the Apple machine. So it is showing you an installed tool chain. I have two channels. One is a stable and a nightly. Forget about this nightly, which we will discuss at a later occasion. Now we are going to use only the stable channel of x86-64 Apple Darwin. That is a host system, and this is a target system, and it is having this x86-64 unknown Linux GNU. So in either you can use a dump machine to see this, but this is an actual representation, the actual representation from the standpoint of Rust. Okay, so now you saw the Restup Show command, and we will again put a cargo-v-build. We will reproduce the error again. So it is asking us to inform Restup to add this target. So let me Restup target add this thing. So it's a habit that I won't copy paste here, but let us Restup add target, and what is required for us is x86-64 unknown Linux. What does it say? Found argument exit, which was not expected or is not valid in this context. Restup target added. Yeah. So it is trying to download this x86-64 unknown Linux GNU from the central repository, and it is install this component now. And if I again issue this command Restup show, and you will see installed targets for active toolchain. One is x84 Apple Darwin, that is the host, and x84-64 unknown Linux GNU. This is the first step. So Restup helps you to add or to remove a tool chain. So that's the reason Restup we call this as a tool chain manager. Let me clear this, and now we'll reissue this cargo -b build -release and target to this x84 unknown Linux GNU. Now we are getting a different error, and errors are our friends, and we can learn a lot from this kind of errors, a page worth of error. So what it says is we have a issue in the linking process, linking with the CC file. So CC, a collection of compiler, and that is being used to do an activity called as linking, which is the part of the compiler pipeline. So in the process of you are creating a executable, one is converting that into some intermediate or intermediate form, where from this will be translated into a byte or a machine code, which is the last mile activity. So in those days, when we create application, we create a .obj file in DOS, and then later we will use a T-link to convert this .obj file into a exe file, which is an executable of DOS and the Windows systems. So similarly, this activity of cargo-b build --release fails at the juncture of linking. So the compilation passed, but it fails when it turns its compiled intermediate representation into an executable one. That is what is the meaning of this. The reason is the CLang, which is a initiative from the LLVM. At this moment, it is not supporting to complete this particular task. Let me stop it there. And so what we can do is we can provide a different linker in lieu of this, or in place of this CLang. So if you run a GCC, for example, which is a collection of compiler, GNOME collection of compiler, it is internally using CLang for this purpose. And if you use a GCC here, this is using the regular GCC. So what we need now is, when we issue this cargo-b build -release, we have to give some suggestion to the cargo. Dear cargo, please don't use a linker that what is already by default you are favoring. You use a linker that what I will supply to you. So that is what is simple thing. So this is something that you have seen that in your life multiple times. There is some default configuration, and naturally every package manager or a toolchain manager creators anticipated this kind of situation. They'll give you some ways to override the default configuration with the one that what you are suggesting. So that is what we are going to do to make this process completed successfully. So let us go back to the plan again. So adding a toolchain to the Restup is done, and we attempted to did a cargo build -release -target to the target environment, which is a triple target. And now we have to reconfigure this cargo to consider our suggestion. So that's what we are going to do, the 9th activity. So how to do that is, if you are using a Apple system, probably you may know that we can download this GCC from browser. So browser install. What is required for us is we need a GCC . So we have this installed already. So what we are trying to install here is, it's not this unknown Linux GNU is not a simple thing. It is having a lot of other things internally. It's a collection of compiler. So it will that may include your a compiler for your Fortran, or for a compiler for anything for C. So for some reasons, it seems in the past I have already installed this. So otherwise, if you require, you can do a brew reinstall. So brew install x86 64 unknown Linux GNU will give you the required artifacts to complete the linking. So we have to use a brew tab also to go to this Sergio Bennett's OSXT, and where this is available. So we are getting this through this tab, and let us check whether it is available in our, normally it will be available in our user local seller. I'll show it where it is. Okay. this. Yes, x86. This pre-installed files. The version is 7.2.0, and this is the GCC. What is the GCC? Yes, this is the GCC we are going to use in place of the CLAN default thing. So let us run this to see this. No input files, compilation terminated. So let us use this. It is just an attempt. So we go back to the place where we have our code and get into the simple. How to do that? This is a little bit tricky. That is how to reconfigure this. So you have to create what this Rust suggested way is that you can have a pet project cargo customization by creating a .cargo directory, and within which you can create a config file, just a regular config file, that's it. And we can copy the path of here. I need to copy the entire path here. Let me again visit this /user /local server x86 7.20, and the pin I have is this is the linker. Okay, so let me just copy this so that we can directly refer this in the linker. Just copy that. Cargo and something about cargo config, and now we are going to copy paste this. So naturally we have to decorate this what it is. So we are telling this as this is a linker, and this is a linker for what we are going to inform this as. When I am calling this as target is this x86 GNU. You use this in place of the regular linker. Now let us check whether this is working. So just I am leaving this to you again. So target x86-64 unknown Linux GNU. If this is a target, then use this linker. That is what is a simple way of informing the cargo. So we are again go to the place where the cargo is placed. Cargo.yml. I'll again issue the great command clear cargo -b for variables, and then build -release target and x84 for this. Cool. It worked. So now you can see that it considered your suggestion, that is what is a linker. It will use what you are offering this as a linker for. So this, let me expand this. See, linker is user local celler x86. So this is earlier it used the CLAN as a linker, the default one, and now we have replaced that with a linker of our choice. Now we go to the target directory of x86. Now you will see this simple, which is an executable. So if you run this executable from here, it should not work because the current architecture of both the machine are the same, but their operating systems are different, which determines the way that it is aligning the machine code in the memory. So dot simple here should give you exact format error because the simple is in a format called as ELF, executable and linkable format, I believe. That is suitable. That is the supported format for Linux, similar to the Mac-O format of Apple Mac and .exe format of Windows. Now we will dispatch this dot simple from here to this place to check whether this works. So now we have a simple already. We will copy this simple also to that particular place. Root, what is this place? Root, so recipe, simple to rootlet. Let me store this as very simple. Okay. So now we have the simple and the V simple, and this V simple is too big now. It is several sizes. It is bigger. We'll try to run this V simple now because we copied this simple from here as V simple. And what is the size here? 32663,696. Okay, so the same bytes. V simple. This works. That's it. So we successfully cross-compiled an artifact that has been created in one host. That is, that one host is the Mac, and we have made it executable in another target. In our case, the other target is a Linux. The same way that you can do between any given targets. Okay. So let us go back to our plan. So we completed the reconfiguration, we completed the build, and we have deployed that also. So now reducing the size of the executable. That is the next activity. So, and uname. So the uname is also having one more thing, uname-m if you provide, to tell you what is the instruction set architecture. And uname alone will tell you the Linux. That is another way that you can guess what is a target triple. Now, what is the next? Yes, strip is a command. It will help you to remove certain debugging symbols and sections. We will try to run this strip on this simple strip debug on this. Now we saw that this simple is now small, and we will run -all, which is another switch. Okay. Which we expect to make this more small. We'll run this. Yes. So 272680 is what is the final count of this, and if you compare this with this 326 slash 272680, and the overall release was reduced by 11 times or 12 times because it's 11.96. So that is a very huge reduction in the byte size. And later we can discuss about how we can optimize the build for a particular purpose, whether it is the trade-off that we can discuss it later, the trade-off between the size and the performance, the other convenience. So everything matters. We'll discuss it on another occasion. So now we will go for a simple recap. So now we have reduced the size. So the recap itself, the plan itself will tell you cargo new, cargo run, cargo build, and a cargo build hyphen release. And you can, when you see this won't work because this has been built for a different purpose. And we understood what is a target triple or a triple target. And we have three things. That is the architecture. The vendor is not relevant here, and the operating system, which is the last segment of this triple target. And we used, if you are in an Apple machine, then you can use a browse to tap and install the respective GCC linker for the purpose of linking, because using the regular CLAN to link this is not working. So that's the reason we take this weird route, otherwise it is not required. And we have added a toolchain to Restup to facilitate the cross-compilation to a different target. So this is a reconfiguration that what we did, we just gave a hint to the cargo about the new linker. So, and then we build and deploy it. So I think that what you can see again is the changes we made to the cargo. So we created a .cargo directory at the place where the cargo.2ml lives, and within this .cargo directory we made a change to the, we offered our suggestion that if you want a linker, you use this linker, and I kept this linker in this location. That is what you are telling to the cargo package manager. Fine. Now we go to this guy. I forgot to tell you a simple thing, that is about the STD, famous STD error. If you run this Restup, stable x86-64. So this is the triple target of this machine. It's a Linux machine. Let me add one more toolchain to this. A famous toolchain, Restup target add. Restup target add. Lesson unknown. Okay, lesson 32. That is for the WebAssembly, which we are going to discuss the next few days. So now you are seeing that it is downloading a version 32 unknown, and the downloading component is Rust STD. Now let us see what happens to our toolchain. Restup Show. Now you are seeing that the x86-64 is also one of the active toolchain, and the version 32 unknown is also another toolchain. So when we, let us remove this version 32 unknown now, or let us heroically remove this x86-64 unknown Linux GNU, so that you can see what happens to the code that what we are running here. So Restup remove, target, remove this guy. So this won't allow you to hereafter perform any operation. Probably you can run this reasonable now, no problem, but when you cargo new test, the main test cannot be used as a package name. Okay, cargo new ABC. So it's created a binary application ABC. Now when you attempt to run this using the cargo run, it will tell you this famous error, cannot find grade for yesterday, because we have just removed it. So if you have this, the respective target toolchain in the environment, then the Rust C can use that to run this program, right? Even to do that with the consolidators, you can see the Cargo and Rustup. So Rust C. So that the error is here that it is unable to find a proper tool chain to complete this job. So whenever you come across with this error, cannot find crate for STD, then you just check what are the tool chain we have. That is so you may be fooled when you are thinking, you may think that it is available, but in fact, it's not available. I accidentally have removed this x86 one day, and I was confused why. I was thinking that it is available here, but it is not getting displayed. The reason is, I guess there is a small defect in the Restup Show activity. Only if you have more than one member, this active toolchain is getting displayed. Now see that it is not displaying the version 32 and unknown. So if you ever come across with this, you try to add one more Restup target add. Now it is installing this x86 which we had removed some time before. Now if you run this Restup show command, it will show both this version 32 unknown and the x86 unknown. So when you accidentally remove any of this active tool chain, add some other tool chain, so that so in essence it is displaying this installed targets, meaning only when it has more than one item, you can see what are the other members here. So when there is only one member, it won't display what actually the active tool chain. Probably this may be resolved in the coming days by Rust. And until this time, don't get fooled that you are having this tool chain installed just by looking into this. So now when we run this, now you can say that it is getting created. So this is a very simple, a quick way to diagnose a problem when you encounter this STD, cannot find the crate for STD. So whenever you encounter this error, cannot find crate for STD, add one more tool chain. If you are unable to see that, then you are certain whether this the tool chain is really part of this active tool chain. Install the targets for this active tool chain is really available, and then you proceed to create the targets in the host platform. Thank you so much for your time, and I guess we have completed our experiment successfully.